Hello everyone. Today we will be presenting our project titled Genetic Programming for Income Classification, completed as part of module Evolutionary Computation and Humanoid Robotics. My name is Ashik Kannambali Janathan and I will be presenting this project along with Sharanya Shalu. In this presentation, I will be walking you through the first part of our work, covering the motivation, the problem we addressed, our preprocessing pipeline, and how we selected genetic programming as our main learning approach. In today's presentation, we will be covering the following topics. We start with the problem statement, followed by steps involved in preprocessing. Then we briefly discuss the dataset features and move on to the model selection, where we explain why genetic programming is a suitable choice. After that, we introduce the GP function set, the overall GP configuration, the fitness function, and our evaluation procedure. We then present the evaluation results, followed by the explainability of the model, and finally we wrap up the conclusion with future scope and reference used in this work. On moving to the problem statement, the goal of this project is to develop a classifier using genetic programming or GP to predict whether an individual income is above a specific threshold. This prediction is based on a variety of demographic and employment related features. For this task, we used a modified version of adult dataset which we obtained from Kaggle. The dataset contained several personal and work-related attributes, and our aim was to evolve GP-based model that can classify income levels accurately. Rather than using traditional machine learning model, we focused on GP because of its evolutionary nature and ability to discover symbolic solutions. So, on moving to data processing. Before training the model, the dataset requires several preprocessing steps. First, the data came already split into training set with labels and test set without labels. We address missing values by replacing any question mark entries with the most frequent value in each column. All categorical features were converted into numerical form using label encoding, as GP requires numerical inputs. For numerical features, we applied standard scalar, which ensure that all variables operate on similar range during evolution. Finally, we performed an 80-20 train validation split on the training data, allowing us to properly evaluate the performance of GP model during development. On moving to the dataset features. The dataset contains a total of 15 input features. These include attributes such as age, work class, education, marital status, occupation, race, sex, capital, capital loss, hours per week, and native country, among others. Our target variable is a binary income label, where the value is either 0 or 1, depending on whether the individual earned above the defined threshold. These features collectively provide a rich set of signals related to income predictions. Now the question is, why genetic programming? For model selection, we choose genetic programming particularly because of its flexibility and its ability to evolve mathematical expressions automatically. GP is particularly powerful when the relationship between features are complex or nonlinear, and when we want the final model to be interpretable. In other ways, we are not just training another black box classifier. We are evolving a symbolic formula that can actually inspect and analyze. Now, looking over to GP's advantages, there are several reasons why GP is suitable for this task. First, it can automatically generate symbolic expression without us needing to define a fixed model structure beforehand. It naturally captures nonlinear interactions between features. It also produces models that are interpretable, meaning we can look at the final expression and understand how it makes predictions. Overall, GP gives us a balance of accuracy, flexibility, and transparency. On moving to the GP's function set, for our GP implementation, we used a set of functions that support stable and effective evolution. This includes standard arithmetic operations such as addition, subtraction, multiplication, and a safe version of division. We also use unary functions including negation, a safe logarithm, and trigonometric functions like sine and cosine. We also allowed to use the use of empirical random constraints, which are small numerical constraints between -1 and 1. All helper functions are designed to avoid numerical error and keep the evolutionary process stable. The remaining slides will be presented by Sharanya.
Hi, I am Sharanya Shalu. From here on, I will continue the presentation. In this part, I will explain the configuration settings we used for the genetic programming model. These parameters define how the algorithm evolves, solution, and directly influence its performance. Let's look at the key settings we used. To begin with, we set the population size to 800. This means each generation contains 800 different candidate solutions. A larger population helps maintain diversity, which increases the chance of finding better solutions. Next, we used 100 generations, which represent how many evolutionary cycles the algorithm goes through. More generation allow the solution to gradually improve and evolve. For genetic operation, we used a crossover probability of 0.9. This means 90% of the time two parent trees will exchange parts of their structure to create new offspring. We also used a mutation probability of 0.4. Mutation introduce more random changes in the trees. This helps the system avoid getting stuck in local optima and keeps the search process creative. To maintain complexity in control, the initial tree depth was allowed to vary between 1 and 7. This ensures the algorithm starts with a mix of simple and moderately complex solutions. During mutation, the trees introduced can have a depth between 0 and 3, and we also set a maximum allowed tree depth of 35. These limits help prevent excessive tree growth, which can make the model slow and harder to interpret. We also used a Hall of Fame size of 15, meaning the best individuals are preserved across generations. This ensures that the strongest solutions are never lost during evolution. Finally, we used a random seed of 42, which ensures reproducibility. Overall, these configuration choices create a balance between exploration and control, helping the genetic programming algorithm evolve effective and efficient solution throughout the training process. In this part, I will explain how we evaluated each genetic programming individual. The fitness function helps us measure how well each GP individual performs the classification task. In our project, we used accuracy as the fitness metric, which simply tells us how many predictions were correct out of the total predictions made. To evaluate each GP individual, we first compare the GP tree into a callable function. This function is then applied to every row in our dataset. For each data point, the tree generates a numerical output. We then convert this output into a class label using a symbol role. If the output is greater than 0, we classify it as class 1, that is, where income greater than 50,000. Otherwise, we classify it as class 0, where the income is less than or equal to 50,000. After generating all predictions, we calculate accuracy using the equation like accuracy is equal to correct predictions divided by total predictions. This accuracy becomes the fitness score of of each GP individuals. By using this fitness function, we encourage the algorithm to evolve individuals that separate the two income classes more effectively. Overall, several generations, the GP model improves by selecting individuals with the highest accuracy. Overall, the fitness function plays a key role in guiding the evolution and help us build a model that classifies income level more accurately. Now let's look a little more deeply into the evaluation process and understand how each GP individually is judged. The first step is to compile the GP tree into a callable function. This basically transforms the evolved tree structure into something that can take input values and produce an output. Next, we applied this function to every row in the training dataset. For each data point, the function generates a numerical value. These output form the basics of our prediction. To convert these output into final class label, we use a simple threshold rule. That is, if the output is greater than 0, we classify it as 1, meaning income greater than 50,000. Or else, if it's 0 or below, we classify it as 0, meaning income less than or equal to 50,000. Once all predictions are generated, we compare them with the actual label in the dataset. From this comparison, we compute the accuracy, which tells us how many predictions were correct. This accuracy becomes the fitness score, and it allows the GP algorithm to identify which individuals are performing well and which ones should be improved or replaced in the next generation. Now let's take a look at the evaluation results of our genetic programming model. On the training dataset, our model achieved an accuracy of 0.8427. This shows that the evolved expression were able to learn meaningful patterns from the data quite well. On the validation dataset, we obtained an accuracy of 0.8349. This is very close to the training accuracy, which suggests that the model generalizes or reasonably well and is not heavily overfitting. Finally, we submitted the prediction to Kaggle to evaluate the model on the unseen test data, and it achieved an accuracy of 0.7747 on the leaderboard. Since Kaggle test data is completely hidden, this score reflects a true real-world performance of our evolved GP model. Overall, the result shows that our GP model worked reliably for income prediction. It performed consistently across training, validation, and test data sets, and it was able to evolve expressions that are both effective and not overly complex. Now let's move on and look at model explainability. One of the biggest advantages of generative programming is that it creates interpretable symbolic expressions. This means we can actually see how the model makes its decisions, unlike many black box models. In our case, the best evolved model combines several types of operations, including simple arithmetic operations, logarithmic transformation, trigonometric functions, and multiple features from the dataset. All of these were brought together into one symbolic expression. The model then produces a numerical output for each data point. To make the final prediction, we use a simple rule. If the output is greater than 0, we classify it as high income. If it is 0 or below, we classify it as low income. Even though the final expression can look complicated, its tree-based structure allows us to trace how each feature contributes to the prediction. This interpretability is a major strength of GP because it helps us understand why the model made a certain decision, giving us much more transparency compared to typical black box models. To conclude, the project demonstrated that generative programming is a strong and effective approach for the income classification task. By evolving symbolic expressions over generation, GP was able to achieve solid performance with a training accuracy of 0.8427, a validation accuracy of 0.8349, and a Kaggle test accuracy of 0.7747. This result shows that the model generalizes well and maintains consistent performance across different datasets. Another key strength of GP is its interpretability. Unlike black box models, the evolved expression allows us to understand how different features contribute to the final prediction. This transparency makes the model not only accurate but also easier to trust and analyze. Overall, the project highlights that GP can successfully produce models that balance predictive performance with interpretability, making it a valuable method for real world classification tasks like income prediction. Moving forward, there are several ways we can improve and extend this work. First, we can explore alternative fitness metrics such as the F1 score. Since datasets like income classification can be imbalanced, using the F1 score could help the model perform better on minority classes and produce more balanced predictions. Second, we can apply feature selection. By reducing the number of input features, we can simplify the GP trees, improve interpretability, and possibly reduce overfitting. Simpler trees also make it easier to understand how specific features influence the final decision. Finally, we can experiment with different function sets and evolutionary strategies. Introducing new mathematical functions or using elitism, where the best individuals are always carried forward, may help the model converge faster and achieve stronger overall performance. These improvements can help make the GP approach even more effective, both in terms of accuracy and clarity of decision making. Here are the main references that supported this work. The first is Introduction to Evolutionary Computing. This book provided the foundational concept of evolutionary algorithm and helped guide the overall design of the GPU system. The second reference is the Handbook of Grammatical Evolution. Although our project focused on generative programming, this handbook offered valuable insights into evolutionary computation techniques and inspired parts of the experimental setup. These references help shape both the theoretical understanding and practical implementation of the project. Okay, now that's the end of the presentation. I appreciate the opportunity to present this work and I hope it gave you a clear understanding of how generative programming was applied in this project. Thank you.